So hello everyone, welcome to the talk. My name is Krystian, this is Panagiotis, and we'll do a retrospective on Julia Web Services today. So first I'll talk about the event that triggered the retrospective, what we did to fix it. I'll go into the details of some of those solutions, and then Panagiotis will talk about HTTP and how we can improve it in Julia. So let's go. The event that triggered this retro was basically a demo that we ran around a year ago, around JuliaCon. So it was a live demo with 50 concurrent users, and it was a Julia-based app. It had a Julia-based backend behind an Nginx reverse proxy, and the application got completely unresponsive once the users actually logged in. So just note it was 50 concurrent users. That's not a lot. And we started thinking like, who's at fault? So there's a list of suspects here and you can make your guesses, but let's just go ahead and see the live view of this event. This was the dev team live cam. Basically, all we saw in the logs was the unable to accept new connection error message. So this is from HTTP.jl, and the clients basically saw no responses. They weren't even coming back to the users, and they were mostly timing out on CloudFront level. So this was a pretty great demo, I must say. I'll go straight to how we approached the fixes, and we started with looking at database performance because that backend was directly connected to a Postgres instance. So this was a pretty legacy backend, so you might see some obvious things here, but we basically changed from libpq execute, which is a sync function, to async execute, and we added a database connection pool. So both of these at the time didn't really bring any big performance improvements. They were mostly just there to assure better concurrency. Then with some optimizations to some of the more commonly used endpoints and some lazy loading that actually works quite well with middleware, we got very modest results, as you can see below. But first, just make sure to use libpq 117 because we found a bug when we changed to async execute, and it's a pretty serious bug, so you probably want your libpq updated. So if you look at the table, you can see the RPS number, so that's requests per second benchmarked with AB. There's 4 examples, 3 of them with database. As you can see, the original numbers were actually quite bad, and we only got a modest improvement of 2 to 3x. So this wasn't nearly what we had hoped for in the beginning. But then I was working on some other things related to this, and it was basically creating a service template to split bigger services into smaller services more easily. And I was trying to replicate the HTTP setup that we had within this legacy service. And once I enabled SSL, I saw the performance just drop significantly. And that was like a red alert in my head. So we basically investigated it, and it turned out the legacy service actually had SSL on just to provide inter-container communication, which wasn't pretty much necessary for us because it ran in the same Docker network, so we could easily remove that. And of course, from the client perspective, the service was still accessible with SSL because it runs through the Nginx reverse proxy. So with that, we have actually seen like huge improvements. And has gotten to the point where the performance is not really a problem at this point in time. So this was a 20-30x improvement across the board. And we did bigger demos since that, and the service has been behaving as expected. You may notice the numbers are not that great, even though we do consider this a win after all, because yeah, we will get to that in the later part with Julia and HTTP performance in general. This isn't the last part of how we fixed this, because of course we introduced some more issues when trying to fix this. While we upgraded to 1.9 just as a maintenance measure and kind of to make sure there's fewer performance issues with the service, we introduced memory usage issues. So I will talk about the details later, but just to confuse me even more, I had two suspects, OpenTelemetry.jl and Kuber.jl, but they were just heavily contributing to the leak and not actually causing it. Turned out to be Julia GC after all. And the intermediate solutions were actually quite confusing as well. I did add a replacement for metrics from OpenTelemetry.jl, and it is a very similar implementation, and it didn't leak, so that was confusing. Then we found a lead that running GC full passes often actually makes the leak go away. So this was quite confusing as well, and we call this, I will call this in the presentation auto GC later. So this just basically means you run GC often. And this is a slide that kind of tells where we are today. So I mentioned the service template, and with the service template, we split off 3 smaller services. So that just allows easier debugging and better scaling in general. We got rid of the memory issues mostly by applying memory limits and this AutoGC strategy. And I noticed after upgrading to 1.10, most of the memory issues are actually gone. So this is certainly an upgrade, and you will see it in the graphs later. Under the line, you can see what we did to keep this issue away. So we do have tracing on all HTTP endpoints. So we do have data to see the timings of all HTTP calls to investigate if there is any regression. We do have custom metrics to keep an eye out on things such as open database connection pools. And of course, we run multi-user performance tests regularly just to catch those nasty situations. So I'll go to the details section. And first off, let's start with the SSL that I already mentioned. You can see the numbers. With SSL off, we have 13,000 requests per second. With SSL on, it's just 50. So this is a huge foot gun. It's maybe a foot shotgun, to be honest. So you should probably not use SSL. And yeah, there is an example where your HTTP server can even lock up completely. So in the second example linked above here. There is a quite confusing setup with HTTP.jl and threads, and Julia 1.9, I think, introduced thread pools. So you do have the interactive thread pool now, and HTTP will run on it. It's just that it makes the situation even more confusing than it already was. So if you launch Julia like this, like threads 2,1, you will have one interactive thread, and HTTP will run on it, as well as the I/O loop, as well as your handlers, because HTTP.jl uses @async to spawn handler tasks instead of threads at spawn, and @async basically glues the task to the thread that it was spawned on. So you may have seen warnings not to use async, and yeah, you should not use async. There is a workaround if you do have heavy handlers that take a lot of time to execute. If you threads at spawn to the default thread pool from the handler, the task will move to the default thread pool. So if you do have a handler that takes, I don't know, a second to run, it's already worthwhile to move it to the default thread pool. Yeah, and you can see the example of how to do it. You just basically spawn and fetch within the handler. So this setup is specifically 2,1, so 2 default threads, 1 interactive thread. I found it to be the performance sweet spot. Not really benchmarking too well, but I am thinking of trying out 2,2, so 2 interactive threads. But so far I have been having like mixed results, so it's not always better. So do your own benchmarking if you are trying to make decisions on how to set this up. Just one just one watch out, your code needs to be multi-threading safe to apply this strategy. If it isn't, you sadly have to run with one thread. So your service should already be concurrency safe, but multi-threading safe is just another level that you have to go to use this effectively. As far as database improvements go, I will speak generally because this doesn't always apply to libpq. But technically, you should always use async interfaces. Sync calls in Julia will block the thread until they return. So it's a huge waste of time. And as the embed TLS example should show you how much of a performance penalty it actually is. Another cool thing we found was that serializing JSON within the SQL query is sometimes faster than doing it in Julia. But that only appeared with huge objects with 1,000 of elements, especially arrays. So you can try it out if you are returning some more data than usual in a specific endpoint. We found a lot of unnecessary database calls in middleware, and you may be surprised how much can sneak up to the middleware. And just try to log every database call that you do, and you will see that you're doing way more of them than you probably should. Some strategies can be applied here, such as lazy loading structs, and this was pretty effective at solving this issue. And obviously optimize your SQL. That's probably the lowest hanging fruit out there if you didn't do this yet. I mentioned memory usage issues, and it seems that this is only happening on 1.9 as far as my research goes. And the behavior is that if you look at GC statistics, the GC works technically fine. But the OS reports huge memory usage, and it just seems that the GC is pretty greedy. Just note that this happens with long-running async loops and big strings specifically, mostly in HTTP handlers, so this is a pretty specific situation. It's not that Julia 1.9 is always leaky, it is leaky in this case, and also note that it's not always leaky in this case, so this is a pretty specific example, although I do have a reproducer with OpenTelemetry.jl. In production, this is mostly observable after weeks or months of runtime, so do keep that in mind, that this is a long-term issue, not really a shortly observable issue. So if you suffer from these issues, just make sure to upgrade to 1.10. And regardless whether that solves your issue or not, you should apply memory limits conservatively. That's pretty easy to do if you run Docker or Kubernetes. I think you can apply memory limits using cgroups in Linux as well. So just make sure to do that, because Julia actually keeps, looks at the memory limit and will try to use as much as memory as it can within the limit. So, and the last resort that you have, so this is for really bad cases, so I don't recommend you do this, but if you can't get rid of your memory leak issue, there's the auto GC strategy, which basically means you have to run GC often. So we run GC after every HTTP call. I will show an example implementation of this later. So right now you can see a graph of memory usage on a container that was a pretty easy case. So 1.9 with no memory limit is just going endlessly up. So without a limit, Julia 1.9 will be super greedy and just take whatever is available and mostly not give it back. If you run GC manually, it might go down a bit, but not always. So just keep that in mind. If you apply the limit, you can see this behavior that the GC just bounces off the top. So that's the middle of the graph. And then 1.10 with the limit applied has a very flat usage. So I'm assuming it is significantly better than 1.9, but as you can see, this is data from June. So this is still pretty early to say, but I hope that the situation is significantly better. This is a container that is actually pretty problematic because using the limits didn't really help. It didn't bounce off the top. Running GC on it manually, triggering it, basically no difference. So only when we deployed AutoGC, it actually behaved correctly. And as you can see, most of the middle of the graph is actually running with AutoGC. And 1.10 seems to be behaving about the same. So this is a pretty big service, and this is actually the legacy service that was causing us issues. So yeah, this is the problematic case. And here's an example of AutoGC implementation. So what you need to know is just that this is a task running in the background that looks at the last time an HTTP call was made, and it will sleep for 5 seconds after that. And if no HTTP call was made during that time, it will run a full GC pass. So this is just hoping that we hit a moment when the HTTP server isn't under load. And we run GC during that time because running GC a full pass is actually quite a bit of a performance degradation. So it waits for all threads to stop, and then it runs GC. So you should not do this often, and you should only use AutoGC if you actually suffer from a heavy case of memory leaks on 1.9. Right. So this was a retro. So let's do some key takeaways. First off, if we tested multi-user scenarios for performance, we would not have had this terrible demo, and so make sure just to do that. I found validating performance after making key changes to be super informative, and you can actually catch a lot of information. That's how I caught this SSL issue. I was just benchmarking the HTTP template, change after change, just to see if there's any difference. And that's how we basically solved most of the performance issues. The hero of this is basically all the metrics, logs, and now traces that we have. Because without this, it's basically impossible to debug such an issue. So just make sure to collect at least logs and metrics. This is pretty easy these days with OpenTelemetry.jl. You can set up Grafana pretty easily. There's other open source alternatives. So make sure you have that definitely. Next, just within the ecosystem, we have a ton of great packages, but you may find some usage of a package that is not really production ready. Maybe it's not multi-threading safe, for example. So just make sure that you are ready to sometimes go ahead and fix some things in a package that you're using. And lastly, we kind of think that what you have seen here should not be an experience of a Julia user setting up an HTTP server, right? All the foot guns, all the issues with defaults, and that should not be happening for a standard user. So we definitely should have better defaults. Just give users decent performance by default instead of allowing them to do a lot of weird stuff that might just ruin their performance in general. So I took most of the stuff that I talked about in this talk and put it in an HTTP server implementation. It's mostly focused on just providing an example implementation. There's a simple setup. There are example handlers on how to pass context properly, how to use threaded spawn. There's an OpenTelemetry.jl setup. I set up Docker files. If you are new to Docker, this will be a good guide on how to actually set this up correctly. There's a memory limit example with Docker and an AutoGC implementation, more than I have shown on the slides because it's actually a bit more complex. And it is threaded by default. So make sure to check it out if you are trying out maybe HTTP.jl or creating a new service, or maybe you're looking for some inspiration for your existing HTTP server. Just have a look at that. And with this, turning over to Panagiotis.
Thank you, Krystian. Okay, so let's get back to the oopsie. Like, you can hear me, right? So who is at fault? Like, we don't want to blame anyone, but Julia, right? Okay, so how do we answer this question? It's not actually easy to say that a program misbehaves. Like, is it Julia or is it the author of, your code? You're responsible for the code you're running. So is it us or is it Julia? Or where is the problem? Where does the problem lie? This is not an easy question. An easier question is, like, is the simple case in Julia to blame, right? I'm a developer and I just want to run the example on the tutorial. Is that bad? And the answer is yes, that's bad, right? Julia is very, very dynamic, threaded, the GC is great, etc. But if you just take the examples, the simple stuff, and you put it somewhere, and you run that as a service, everything is wrong, as Krystian said. So on a different work stream, like we run the framework benchmarks, which is like a package that tries to standardize like how you test web frameworks. And if you put the defaults there for Julia, it doesn't even run. Like, it doesn't even run fast enough for the benchmark to be included in the final test set. And the Oxygen folks, I don't know if you have anyone here, are doing a second iteration. I'm not sure if that passed. I'm pretty sure it won't pass for the reasons why, mostly what Krystian discussed, but let's take a quick look. So the analysis I'm going to talk about is from this thread that you can take a look at. It's on Discourse. And basically the analysis, this analysis says that it's not really running fast, okay? And the question is why? Actually, let's take a step back. Like, why are we in this situation where a web service with 50 users doesn't run? Like, why is it bad? And the answer is, no one is doing that. Like, there are 3 companies that do that. Like, it's my problem, Krystian's problem, and I don't know, 3 other people in the world. No one is running Julia for web services. Like 60% of the people I asked, of 55 voters, don't do that. And another 29 don't have enough traffic. So if you have one request, like if you run an analysis, an MTK model, and you just wait for data and then you reply, and that's like 1 response every 10 minutes, then you don't care about the decryption taking a second, right? So yeah, 2 people said that they agree. Like maybe it's 4 people, 9%. 1 is me, so it doesn't really count. Anyway, so the defaults. Why are we saying that these defaults are wrong? Okay, and I'm probably getting out of the screen, so I'm not going to go there. So the setup Krystian showed has 2 interactive threads and 2 default threads, right? What problems can you have when you run code? When we say that when you get into a C call, everything blocks, like I don't know if you can grasp right now how catastrophic that is. Like when Julia goes away and decrypts something for a second, the scheduler doesn't run, I/O doesn't run on any thread. You may think that you are sleeping, but you're not sleeping. You are in a coma. Okay, and that's different. Yeah, because when you sleep on a file read, other things can run, timers can run, right? When you sleep on embed DLS, do handshake, nothing runs. when you sleep on a libpq query, not the async version, the sync version, nothing runs. The scheduler doesn't run. And what is the default, right? You run Julia. It's one thread. That's it. So I/O is there, schedulers are there, everything is there. So the defaults don't work. Okay. So what do we suggest? We suggest 4 threads, two thread pools, right? One out of the interactive pool, you will have one thread that does I/O. It should not precompile. liblLLVM will also block you. Like, blocking means that nothing runs. If you block on thread 1, the scheduler won't run. Maybe that changed in 1.11, I'm not sure. But the scheduler doesn't run means that the threads will yield and then wait for thread 1 to start re-waking them up. Like, this is very catastrophic. This is why you got the 999. The 999 error you saw where in the this is fine meme means that there are 512 connections waiting on the socket, right? How can... You can get in that situation if Julia is in a coma. And Julia gets in a coma if you do a blocking C call, right? So precompilation is a blocking C call. You can do a precompilation in another thread. So if something precompiles, send it thread.spawn it. Look at the template. So if you do spawn interactive, in Julia 1.11, it will always run on the second thread or another thread because the thread that runs I/O is out of the interactive thread pool, right? And we hope that the thread that does I/O gets, its own land. But basically, this small table says like where you should put your threads in order for stuff to work. Now, you will notice the question mark here, like where do I put the HTTP server? And the answer, like this is what Krystian said, that the results are not clear. The results are not clear because if you do something heavy in the HTTP on thread 1, then it may interact with other threads I/O. Because remember that all the threads I/O go to thread 1, right? So if your handlers are heavy by themselves, not the calls they do, then it will interfere with the I/O of the other threads. You probably don't want that if you have something that long running. If you don't have something that long running and you don't do much I/O, just leave everything on thread 1. So the gist of it is better defaults, right? We should not be thinking about this. We should be thinking about input and output. Now there are a lot of ideas on how we can improve that, like not doing I/O in Julia, basically. And that's all. Thank you, Michael.
Yeah, I think we have room for one question. Any question?
So you mentioned that the Julia scheduler basically does absolutely nothing if you go to a blocking C call. In what classifies as a blocking C call? What would it be? Could you also, for example, could this also happen in numerical code or something?
Any C call. The difference between async interfaces and sync is that async just return immediately, and then you like kind of ask again, or the other process call. I mean, you just get a call back basically. But any C call is blocking. It just matters, how long it is. So that's basically the general answer.
I can read on that a bit. So basically, if you do a lot of things do C calls, right? BLAS is a C call. The problem is when the C call doesn't return until it does some I/O. Right, so liblLLVM will return to you, I think, like Jeff can, correct me here, but it will return to you after it has written some files. Disaster. libpq.query, like the default way to just read a SQL string, you get the pointer back from the C call after it has a string to return to you, which is not what you want. The async version of that, is much less catastrophic. It says, I want you to take this pointer, it's yours now, and just read it and do the query and tell me when it's ready. And then you wait on a file. Note that this has a 3 millisecond overhead, like that you pay all the time. A SQL that just returns might be faster. So the async query interface, and with that PR that we have in libpq, is slower if the database is in the same machine, like always there. Because it needs to do that, there is a dance with files that you wait on the file to be read-ready, right? But the point is that if you don't go on the async way, which is more expensive in the general case, right? You are vulnerable to catastrophic comatose situations, right? Because if Postgres goes down, you don't run the scheduler, right? Tasks will yield and wait. And then you have these 43 responses per second in the slide with the embed TLS. So you want to avoid the comatose situation in any scenarios. Thank you.
Yeah, and thank you for our speakers for such talk. Yeah, I hope we will find more Genie peaks to run HTTP servers at Julia. Yeah, round of applause.